Tomorrow you'll be designing a container that will keep an egg from breaking when it's dropped. Now let's talk about impulse and momentum and how those will affect how you make your egg drop container. We are on page 3 of these notes down at the bottom. Momentum is mass times velocity. Momentum is mass in motion. It tells how hard a moving object is to stop. If an object is not moving, it can't have any momentum because it has to have velocity, a speed, to have momentum. Notice that the letter P stands for momentum. That's actually the Greek letter rho, but that's okay, it's a P. And when you look at your reference table to find this formula, you need to be careful about which one you look at. Here's the formula, P equals m times v, and this P stands for momentum. Now, right across from this P, there's another P. This is a capital P. This one was a lowercase p. See the problem? And this P stands for power. So be careful. Don't get these two mixed up. In fact, on the test, I would immediately connect these two P's with lines so you'll know which one is which, and you will use this one, the correct one, for momentum. So for an object to have a lot of momentum, it has to have a lot of mass. In other words, it has to be heavy. And it has to have a lot of velocity. That means it has to be moving fast. So if it's heavy and fast, it will have a lot of momentum. For example, a heavily loaded truck has a whole lot more momentum than a lightly loaded truck. The heavily loaded truck weighs more, and it's harder to stop. The lightly loaded truck weighs less, and it's easier to stop. Also, the speed of something affects the momentum. For example, a bug can hurt you if it's going fast enough. If you stick your hand out the window and a bug smacks into it, or if you're riding a bicycle or a motorcycle, oh my goodness, those bugs can hurt. But normally, a bug would never hurt you. It's just that you're going so fast that the bug hits you at a very fast rate, or maybe you hit the bug at a fast rate. I guess it's a little of both. But that is what causes it to hurt so much, because of the momentum of the bug. Impulse is force times time. Impulse is a change in momentum. When the momentum changes very quickly, there's a lot of force. If the momentum changes slowly, there's a lot less force. So in this case, if you're trying not to break your egg, you want the egg to have the least amount of force possible, so you want it to have the longest time of impact. The longer it takes to hit, the more gentle the hit is. For example, if you jump on a soft bed, the bed slowly compresses over time. It extends how fast you hit over a time as it compresses. That longer time means there's a lot less force on your body. Whereas if you would jump and land on the pavement doesn't give, so you come to a stop very quickly. The time of impact is very quick. It's not spread out the way a mattress would cushion it. And therefore, there's a lot more force and it's going to hurt more. So the same thing with your egg. You'll want it to have a lot of cushioning to slow down its time of impact. Now, if you have a big stack of papers, that's not going to slow it down because it's just going to hit the paper like it would hit concrete. But crumpled up papers will slow down the balloon quite effectively because they crumple more. There's some air space in between them, and that allows the time of impact to be extended, which lowers the force. You will also want to decrease the momentum of the egg. You'll want your container to not be super heavy, and you'll also want to slow down the velocity or the speed. You will do this by increasing the air resistance of your egg drop container. So once again, this is why an egg breaks when we drop it. It accelerates as it falls, and it's going faster and faster the further it falls. That's why if you drop an egg this far onto the countertop, it may or may not break. But if you drop it this far, it's likely to break, and if you drop it even from higher, it's very likely to break because it goes faster and faster as it falls. Then, If you drop the egg onto a hard counter, it comes to a stop very quickly. There's a lot of force, and the egg breaks. Versus if it comes to a stop over time on some cushioning, then the force is spread out and is much less. This is the same principle as your seat belt. The seat belt extends the time over which you come to a stop. Instead of hurling forward and coming to a stop against the steering wheel or the windshield, instead the seat belt catches you and slows you down over time. The same with an airbag. The airbag compresses more than the steering wheel does and extends the time of impact to decrease the force on you. Next, we're going to talk about the law of conservation of momentum. Momentum is conserved. If no net force acts on a system, then the total momentum does not change. So, if there aren't any outside forces, momentum stays the same. So the loss of momentum of one part of a system equals the gain in momentum of another part of a system. Let's look at what that means. This is a picture from your Prentice Hall textbook. In this picture, both cars are moving. One's going 10 meters per second and the other's going 5 meters per second. When this car hits this one, it transfers the momentum to the first car, assuming that the cars weigh equal amounts. Then this car is now going 5 meters per second and this car is now going 10. So the total momentum was conserved. Here, only one car is moving. This car is sitting still. These are train cars, by the way. So this one knocks into this one and transfers its momentum to the second car. What if the cars stick together? Well, if they weigh equal amounts and one car is going 10 meters per second and one is not moving, once they connect together they will go half the speed of 5 meters per second. Let me show you this with some golf balls. If you have some golf balls, you might want to try this at home. Have one sit still and hit the other with the first one. You'll notice that the momentum was transferred from one to the other. Mostly, it wasn't perfect, but it was still a good illustration. What if one ball is moving and the other hits it from behind? Did you see how the front one sped up when the back one hit it? So the momentum was transferred from the back one to the front one.